Welcome students to Control Systems 3 Lecture 0. We'll first begin by um, explaining the terminology that we're going to be using in this course, as well as moving on to typical examples of control systems, and finally looking at the control systems procedure. So this is very much an introductory lecture to explain the basic concepts and to review some of the information that you might have learned from control systems too. So the first thing, before we even talk about control systems, we need to relook at our definition for a system. First of all, what is a system? So a system, one of the common definitions of a system is that a system is typically a set of interconnected elements working together for a common purpose. So we see that it has elements and it has purpose. Now, a system can be as complex as an aeroplane with multiple subsystems within it, or it can be as complex as and as big as a chemical plant, like your Sasolburg plant, which you see, which is close to our campus, or one of the other chemical plants which is in next to the Secunda campus. So the system can be that complex, and the interconnected elements in this case for an aeroplane, it might be, as you can see, an aeroplane, for instance, it has engines, and then it has a fuselage where people sit, and of course inside the cockpit there will be some instrumentation which is linked to all of these other subsystems. So they are interconnected in that sense. So a system, on the other hand, can be as simple as a simple resistor in itself, in which case this system can be uh, as simple as a single element. Um, so you would notice that in an example of an aeroplane, the purpose of an aeroplane is so that it can fly people from one point to another. So there is a purpose why the system is there. A system of and in this example, a chemical plant would be to get input in the form of a raw chemical and to produce multiple outputs out of that. So there is a purpose in terms of system. The resistor, on the other hand, we know what the resistor actually does. It actually, you can view a resistor, for example, as a conversion element whereby the current that passes through the resistor is converted into a voltage drop across the resistor. So it does have a purpose or a function in that sense. So what we learn here in actual fact is that a system, it can simply be it's defined as simply a set of interconnected elements working together for a common purpose. A system can have multiple, it can be as big as a chemical plant, or it can be as small or as simple as a resistor. And in all of these cases, the system would be functioning with a single purpose. So moving on, we can look at the two typical types of systems that we have. The first type of a system would be an automobile or simply a car. The second type of system that we may have interacted with or have been exposed to would be a solar PV system or an electrical system. If you look at a car in this case, you will see that the system in itself has subsystems. So it's complex in the sense that it would have a powertrain, an infotainment system, whereby it has a radio, music system, navigation, GPS, and then you might have an electronic brake system. In fact, you must have electronic brake system for safety. You would have the body of the car, which would have power windows, it would have doors, it would have seats, controls of mirrors and motors. You would also have some safety subsystems, airbags, collision warning, parking assistance, motion and night vision. So the system, an automobile itself, can have subsystems. The powertrain itself would be a system, and then you have its own set of interconnected elements. So you have a fuel injection system, which might have a pump inside, a pump linked to a certain controller. This in itself would be a system, but it's also made up of when it's connected to other systems such as the infotainment system, they make a bigger system, which is um, a modern day car. Now, another example here would be a solar PV system. A solar PV system, you would have in this case one element which is the PV modules. You would have one element which is PV modules. Now, the PV modules would operate to charge the battery, so they would stop. They would operate to charge the battery with the assistance or under the direction of a charge controller. Note this word controller, which we're going to be dealing with a lot. And then this would be then mounted to an AC load, which would be obtaining electricity from the PV system. Now, the system in itself, the PV system, as we can see, the solar PV system, has a purpose. The purpose of the PV system is to provide electricity by generating electricity by harvesting electricity from the sun. So that would be the purpose of the system. The other type of system, which is an automobile system, the purpose of the system, obviously in this case, would be to carry passengers from one point to another safely. Given the variation that we expect to get from typical systems, we have to have a common way of viewing all of these different types of systems. We have to have a common way of abstracting the different types of systems that we see, be it an aeroplane or as simple as a simple resistor. So we have noticed, in fact, from the previous module, that a system can be viewed as a block. Basically, we can view a system as a simple block. A system can be viewed as a block with a set of inputs and a corresponding set of outputs. Additionally to this, we can view a system as having an internal state, the state of the system. For example, of our terminology, we will say then the inputs of the system, it's what we call the manipulated variables, what we can change. And the outputs would be the controlled variables, what response we get from the system. So, for instance, if you look at a pot which you use for boiling water as a system, the input would be the heat, which is the manipulated variable. So you can manipulate the heat, and then the output would be the temperature of the water. So in this case, the system in itself can be viewed also to be having a certain state. A certain state in the sense that the current temperature of the water has an influence of how the system will respond. If the water is already hot, then you need a little bit of extra heat to make sure that the system now takes the temperature to a certain high temperature. However, if you put ice into the pot, then that will also influence the output that you're going to get, given the same amount of temperature. So the internal state of the system is also important. We will later see now how the different views of the system can be used to model a system. Now, a system whose output we wish to control, typically a system whose output we wish to control, we will call a process or a plant. This is the terminology that you will see or you would have seen. And now a control system in this case then becomes an interconnection of components forming a system configuration that will provide a desired response. So I know it may sound similar to the system itself, an explanation of system. So a control system is a system of systems, an interconnection of systems that is set up so that we are able to get a desired response out of the whole setup. Now having defined that system, we will therefore look at the different kinds of systems that we may see, so as to then explain the components that we see in typical systems. Take, for example, the house lights. Now, in the house lights, we see that this can be viewed also as a system, because in this case, you have different components on how to operate the system. So you have the house lights, which are in the background connected to a switch, and you are able to operate the system or control the system by simply touching the switch. You are able to turn off or on the house lights. In this case, you have a desired output that you wish. If you want to turn off the lights, you want the lights to be on, and that output you will observe by the bright light that you will get out of the system. The process in this case would be your lights. That is the system which you wish to control. And the controller would be the other subsystem which you use to make sure that you get the desired output. In this case, your hand will be the controller. Now, you will notice that in most of these cases, there has to be an intermediary system, which typically is called an actuator, which will be used to link the controller, or to send an instruction, a control signal from the controller to the process. So the controller in this case is what formulates the desired control signal. So your hand formulates that desired by switching on the switch, and the actuator performs the required signal conversion. So your motion of pressing the switch is converted into an electrical current, that because the switch closes a circuit, and then this is converted into an electrical current in order to give you the desired output. So sometimes you will notice that the actuator in itself is considered, or is assumed to be part of the process. So sometimes the process in itself will be defined as the actuator plus the process. So sometimes the switch plus the light will be just viewed as the process in some of the definitions. So sometimes it's very hard to separate the actuator from the processes in itself. Now, what we are observing here, actually, the series of cause and effect from the desired output response through to the controller, sending the signal to the actuator sending it to the process to be giving you the desired output. This is a type of what we call an open loop control system. An open loop control system is a system which simply controls the process without any feedback. So you have an input. We have in this case a desired output response that is taken by the controller to formulate the control signal, and that control signal is applied to the actuator. The actuator then converts the signal to something that the process would understand to give out the desired output. So we say then an open loop type of control system is the house lights, and the process in this case we say it's an open loop because it operates without what's called feedback. We'll later define this feedback. Another type of system in this case, it's if you imagine manual control or manual tuning of a radio. So you will notice that in a car, for instance, or this old type of radios, you will see that there would be a dial which you can use to tune your radio to your favorite radio station. Let's say you at one point want to tune your radio to 103.6 megahertz. which is your favorite radio station. Now, what would happen is the system would have a certain state. Maybe the system is on 88 megahertz currently. Now, because you want to listen to your music at what do you call 103.7 megahertz, what you would do is you would use your eyes together with your ears. In this case, you would tune or turn on this turn the tuning knob up until your ear can sense that you have correctly placed the receiver in tune with the radio station that you want. So you will notice that when you tune the radio, you might tune it up until to a point where it goes beyond the desired 103.6, where it might give you a noisy signal. Then you have to tune it back to the right frequency. So in this case, each and every time you're tuning, you are also using your ear to validate whether the radio has been tuned to the desired frequency that you want. Now, this is an example of what's called a closed loop system, because each time you control you effect the control, you manipulate that manipulated variable. You at the same time you use a sensor, in this case, which is the ear, to get feedback to understand if you have reached the desired frequency. Now, the whole system can be drawn as follows. So in this case, your hand would be the controller, and then the radio plus the knob that you're tuning would be seen as the plant or the process. Now, because you are tuning in this radio, you are turning the knob. As you're turning the knob, you're also listening to the type of music that you're hearing from the radio, and you're using that music to compare it to what you're desiring, which is the sound of your favorite radio station. And that information, whether or not you are hearing a clearer sound or not, you use that information to further effect another control action so that we can get to the radio station. So in this case, instead of having simply an open loop, you have a closed loop system, whereby you have your controller, in this case, which is your hand, you have an actuator, in this case, which is a tuning knob, and then you have the process, which is the radio. And from there, you have the sound of music which you are listening to, and you have your sensor, which is your ear. Your sensor is measuring the output, which is the sound it hears, and that sound is compared to what you desire, which is the sound of music that you want playing. And from there, you can make judgment as to how far, whether to tune your radio to the left or to the right. This is an example of what's called a closed loop system. So we have now seen that we can have two different types of control systems. The first being an open loop type of system. The second being a closed loop type of a control system. One may wonder then, why is feedback necessary in control systems? Now, there are three main reasons why we would like to have feedback most of the time in control systems. The first major reason for this would be the fact that in control systems applications, there is almost always some modeling error. Whenever we derive a model for our system, there is almost always modeling error. Now, the other third reason why we might want to have feedback is because we want to deal with disturbances. It's because we want to deal with disturbances. The other type is because we want to deal with measurement noise. So as you will see, these three issues are inevitable in real-world applications of control systems. These are all inevitable. So in order to deal with these three main issues, we need a feedback system. And so if we were to then add these three issues, we will see therefore that the disturbance in this case would be in a form of an unwanted input which affects the process, and then that would then be able to affect the actual output of the process. An example would be in a case whereby one is monitoring water level in a tank and there is a leakage. Because there is a leakage in the water, the system, which would be the tank, would not operate according to what basically the model says. And then another unwanted issue that we want to do within the process model itself. So the process model, in the case of a tank, for instance, we would want to have a good measurement or the dimensions such as the cross-sectional area or the height of the tank. But sometimes there are cases where the process can be modeled accurately enough. Maybe it's inaccessible for engineers and technicians to assess. So it's almost impossible to model it. Another is because of complexity. The system may be too complex to model accurately. And another, as we'll learn later, is because the system in itself may be non-linear, whereas the type of controllers that we are looking to learn in this module, or most of what's being used in the industry, it's linear controllers. Now, another source of discomfort in this case that we want to deal with is measurement noise. So basically, measurement noise, when you have your sensor in a previous example of our audio system where we are tuning the radio, the noise then would be the unwanted signal that we'll be picking up from our radio. Sometimes that noise would mix into the desired sound that we want to hear, and it will impede us from making a good judgment as to whether we have reached the station or not, because it's noisy. A common source of noise would be, in fact, by definition, the noise will just be any unwanted signal from the environment, which we obtain, which mixes with the actual signal that we want when measuring. So the noise is always associated in control systems with the measurement. A good example is this electromagnetic interference that we may get from spurious signal. Maybe your Wi-Fi is interfering with the wireless signal of your radio sensor, and that may be a typical form of noise, because we know that there are some other signals which might be broadcasting at the same frequency as your desired signal. So those unwanted signals will then be called noise. So to recap, it means therefore we need feedback in control systems because of three reasons. The first being to deal with modeling error, the second being to reject disturbances, and the third being to remove or to deal with measurement noise. So all of this time we have been talking about two key elements which are important, additional to the in fact in the control loops, and these two key elements are sensors and actuators. So I would like to say a bit more about sensors and actuators. So we have seen that, in fact, for an actuator, we can define an actuator as an element or a system that converts a low powered control input signal to a high powered output. In this case, we said sometimes the actuator can be taken as part of the process. So you may see that this may be called part of the plant or the process in itself, without having to include it explicitly. Now, so a good example of an actuator in this case would be a motor. On a motor pump system, this would be the motor. So in this case here, you have a motor which is linked to a pump. So this would be the pump. Now, what happens here is that there will be an electrical input into the motor, which tells the motor to spin. And as the motor spins, this will be pumping fluid from one end to another. So the input signal, which is a small electrical signal or a low energy electrical signal, is then used and converted used by these actuators, the motor, to control, to create a motion signal, in this case, a movement that will pump, to spin and pump water, whatever chemical that you have in this case. Another typical example would be an electric valve. An electric valve would look like that. So in an electric valve, the piping here, the electric valve can be controlled by inputting an electrical signal into the valve in order to shut or to open for the fluid that we pass it through the valve. So in this case, you will see that in our application, the low powered signal is mostly electrical, but it can be pneumatic in process control. It can be also hydraulic. And so this low power signal will be used by the actuator to convert it into another higher power output signal, which would typically be of a different type. So here you have an electrical being converted to electrical energy being converted to mechanical energy, which is rotational energy. And now, speaking about the sensors, so sensors are the other type of subsystem in a control system, which we need in order for us to get feedback information. So a sensor, what it is that it's a typical subsystem which converts energy from a physical variable into a suitable form. So this suitable form might be, in most cases, it needs to be electrical. In our example, so a good example here would be, for example, a thermocouple. A thermocouple then converts the temperature that's on the rod. It converts it into an electrical signal. So the value of the temperature that it senses from the environment, the process or the plant, it's converted to electrical input, which goes then to the controller to formulate an error signal, so that the controller can be able to make a decision whether the desired level of temperature has been reached. Another interesting type of sensor would be, in this case, a tachometer. So this tachometer, what a tachometer simply does is it converts a signal of motion, in this case the rotational motion of a motor. It converts that into an electrical signal, in this case, which is what is being displayed here on the tachometer. So it can convert that motion into an electrical signal. So basically it does, in fact, the opposite of what the motor does. And sometimes the sensor can be as simple as a light dependent resistor, an LDR. A light dependent resistor simply does it detects the amount of light that's available around it. So in this case, it simply converts that amount of light into an equivalent value of resistance. So the resistance of the light dependent resistor is related to the amount of light that is exposed to. So in that case, the sensors, all of these sensors are able to convert the energy from a physical or environmental variable into a suitable form. In this case, these ones are converted into electrical energy. This one is converted into some form of resistance, which also can be, if you pass current through it, it can be electrical energy as well. Now, going a bit further, you would notice that in some of these control systems, you can have a multi-loop feedback system. So in this case, instead of just having one feedback loop, you might find that you have an inner loop and an outer loop of the system. So this would be a different type of configuration of a system. We will not be dealing with such systems in this module, but it's good to be aware that control systems themselves can be complex in the sense that they could be multi-loop systems. So you could have a loop which would be a controller at a lower level controlling a certain single variable, and then you have a bigger loop of a controller at a higher level, a supervisory level, controlling controlling the same variable or directing it. And then on top of that, we will later learn obviously that whenever the system is it's complex, you might have what you call a multi-variable system. A multi-variable system, in this case, there will be a number of desired outputs, desired responses that you might have in your system. So if you imagine in the case of a chemical plant, you may want to have from say a single chemical plant, you may want to have in this case you may want to have your output being a desired amount of diesel, desired amount in the fractional distillation, desired amount of petrol, desired amount of kerosene. So you have multiple inputs that you want out of your system, and you are sensing all of them. And at the same time, the controller is able to calculate the error signal from all of them, and it's able to send signal to all the actuator, which also has multiple outputs. So in this case, this would be a typical example of a three variable system, as you can see. So systems, control systems themselves can also be that complex based on how complex the process is and the approach at which the approach within which the control system has been designed. So a good illustration, another good illustration example of a control system would be a car steering control problem. So imagine we have a car, which is a typical example. So the aim here is that the driver desires to steer the car or to drive the car over a certain period of time while remaining within her lane. So this driver wants to drive this vehicle so that she can remain within a lane. This is an example of a control system application. So the car would have a desired direction, which is basically to stay around in the middle of the lane, but it may have from time to time, as the driver loses concentration, they may deviate from that, and then the driver would then need to correct that deviation. Or as the road winds round and round, the driver needs to steer it so that the car will remain within the desired lane. So if you look at, for instance, the actual direction that has been traveled, it may be slightly different from the desired direction. So the driver always tries to correct, to go to the correct to go as close as possible to the desired travel direction, as much as the fact that the road is winding keeps on fighting against and to deviate from that, fighting against what the driver is doing to deviate from the desired direction. Now, if you look at that type of car steering control system, we can draw then a block diagram that this is in fact a closed loop, a type of a closed loop control system. In this case, the controller would be the driver. The process that's being controlled is the car itself. The actuator would be the steering mechanism. Remember, the steering mechanism in this case, it converts from, because some of these cars would have a power steering. So the driver would simply steer a little bit on the steering, and then that will then be amplified so that the wheels are turned. So this would be the actuator. So it would convert, therefore, the small amount of power, the motion, the small mechanical energy that's being put by the driver on the steering is converted into a larger amount of mechanical energy to convert to steer the wheels of the car so that the car stays within its lane. And in this case, the sensors which the system would be using would be the driver's eyes. So the driver can sense if they are going out of the lane by simply looking at the lane markings, and they can tell if the car now is trying to veer off the lane. So in this case, we have the driver effecting a control signal, and the control signal is put on the steering mechanism, and the steering mechanism turns the wheels of the automobile so that the car will stay on the as close as possible to the desired course, so the actual course. Then what the driver will do will simply look at what the car is doing to sense or to measure how far off the desired signal will be, and then the desired direction will then be compared to the actual direction, which is measured by the driver's eyes. So the driver can make another important decision on the control signal they need to do. So if the car is it's moving towards the left, then the driver changes it so that they can steer it towards the right a little bit more. So moving on, talking about the last part of this, the last part of our lecture, which is in this case the control system design process. We will notice that in terms of control systems, there are different roles between what an engineer would do and what typically a technician would do. In this case, the engineer's purpose would be to design a control system, and the technician would be the day-to-day operator of the control system. So before, in fact, we talk about the design of a control system, let's talk about general what design means. What does it mean to say there is a design or you're designing something? So in this case, what it actually means is that the process of design is to conceive, or the process of inventing a structure, components, and details of a system to achieve a specific purpose, right? So basically, it's to conceive a system. That is what the design is all about, and the design has to achieve a specific purposes. So the design hinges upon, or it relies upon, a set of key specifications. So specifications of a system, of a control systems, are key whenever you want to design a control system. So the specifications effectively tell us what the system is supposed to do. So the design process is a process of trade-offs. So you may want to, for instance, have to design the perfect car which drives itself, which has tires that never wear out, which has fuel that never gets finished, and so on and so forth. However, the designer always has to settle for a system that's good enough, because remember, this is a trade-off. A trade-off between, if you wanted to design the best car, it means you need more time, which typically you wouldn't have in any case in the world. So you would need to design within the constraints of a time limit. You would also need to design within the cost limit, because you can't just design the best car possible. This might be too costly for people to buy. You also have the more components you put into a system, you might have an overly complex system which you might not be able to control. So design is a trade-off. You need to have a trade-off in terms of time, the cost, and complexity. And also, it's also important to note that design is a risk-taking activity, because in any design there are always unintended consequences, especially when the system that's been designed it's complex. A typical example that we might be familiar with is the Gauteng e-toll system. So, for instance, in the Gauteng e-toll system, this is some of the best technology that's there in terms of capturing the plate numbers of systems of cars that pass under the toll. And then the system is so smart that it uses some form of artificial intelligence to recognize the plate numbers, and then it automatically bills people. So it sends bills to people automatically. It doesn't need a lot of human intervention. So it's one of those best systems that you may have in the world. However, as you might have noticed, that it is a lot of social resistance against this very expensive, very good, technically good engineering project. So as much as you design, you have the design process is risk taking. So because there are some aspects that you may, or a designer may not understand what they're designing, that may later tend to be fatal to the operation of the system. And the design of the system requires engineering analysis. So the main objective of this course is to teach as much as possible in terms of engineering analysis of control systems. So the operator or the technician in this case, speaking from a technician's point of view, who needs to be the operator of the system, they need therefore, in terms of control system, to be aware of this, to be aware of the fact that when the designers of the system were designing the system, they had trade-offs to make, so they can't design the best system. There are also unintended consequences which the designer may not have thought of. So the operator needs to be aware of this, all of these issues, which is why we, as prospective technicians, need to learn the control system design procedure to understand it. So the control systems design procedure, in this case, can be a simple process which is systematic and is made up of multiple steps. So in this case, you would have the first issue with the first thing that the designer would think about is to establish the goals, the control goals. What are the goals of the control system that they are designing? To identify the variables that need to be controlled. This would be the controlled variables, and write therefore the specification. What is the specification of the system? Now establish the configuration of the system. Is it going to be an open loop, closed loop? Is it going to be multivariable, or is it going to be a multiple loop, a feedback system, and the likes? And then obtain the model of the process, understand the actuators that are needed, the sensors that are required. From there, they need to describe the controller and select key parameters to be adjusted in the controller. So you design the controller, and then from there, the system needs to have the parameters of the controller being optimized and analyzed. The performance has to be analyzed, and then if the performance meets specifications, then the design would be considered to have been complete, because now we know what the specifications are. However, if the design does not meet the specification, then it goes back to re-evaluate it, maybe to change the configuration and look at alternative process models, actuator sensors, so that the desired performance of the system can be obtained. So the process can therefore be interactive. From our analysis as future operators of control systems, we can see that this design process has three key phases. So we notice that the first key phase here is to establish goals, variables to be controlled, and the specifications, right? The second key issue here is to have the definition of the system and the model of the system. And the third issue here is to have a control system design and be able to simulate and analyze it. And all of these key aspects we would want to consider in the rest of the course. So the operator in this case, which is our case, we need to be aware of the first issue, which is to establish the goals, the variables to be controlled. That is, we need to understand what the control system was supposed to do. What was the design objective of this control system? So that we can be able to know what are the important variables to look at, what are the set points. So the operator would be interested in that. The second issue is the definition of the system and the model. You know, how does we need to understand what is the structure of the plant? You know, how is this? What is the type of the model? What are the type of the system properties? Is it linear? Is it non-linear? How does it behave? We need to understand that. What is the structure of the system? The other objective is now, how does the system behave? The control system of the plant behaves. We need to know which parameters are important. How does it respond to certain inputs? So by understanding this design control system design procedure, we will then be able to better do our job as control systems operators. So having looked at all of these issues, it's important to also reflect back on the learning objectives of this lecture 0, which is the introduction. So by the end of this lecture, you should be able to describe the different elements, signals of a control system. Feedback loop, you should be able to know what the noise, what measurement noise is, where the error signal is, what is the set point, what would typically constitute a controller, what would be an actuator, the process, and the sensor in a system. So you should be able to describe those different elements, given a case of a type of a control system. You should also be able to analyze the operation of a practical control system, such as a car steering system, and be able to identify those elements within that practical control system.